Look up at the night sky tonight, and you will see it there, just as it has always been. The moon, our gentle companion, soft and silver, hanging in the darkness like a quiet lantern. It has watched over sleeping cities and quiet forests for as long as humans have walked the earth. And if you look closely, you will notice something familiar about its face. The same craters, the same shadows, the same patterns of light and dark that you saw last night, and the night before, and every single night of your life. We always see the same side of the moon. Always. No matter where you stand on Earth, no matter what time of year it is, the moon shows us only one face. Its other side remains forever hidden, turned away from our view as if it is keeping a secret. And this brings us to a gentle puzzle, a question that might drift through your mind as you watch the moon rise over the trees. If we only ever see one side of the moon, does that mean it is not spinning at all? Is the moon just floating there, perfectly still, like a painting hung in the sky? The answer, as you might have guessed, is both simple and beautiful. The moon is spinning, it turns and rotates, just like the Earth does. But here's the strange truth. The moon spins at exactly the same speed that it travels around the Earth. One full rotation takes exactly the same amount of time as one full orbit. And because of this perfect match, the same side of the moon always faces us. It is not that the moon is frozen in place. It is that the moon has learned to dance in perfect step with the Earth. This is no accident. This perfect timing, this quiet synchronization did not happen by chance. It is the result of a cosmic force that has been working for billions of years. A force so gentle, so patient, that it shaped the moon without anyone noticing. That force is gravity. And the phenomenon it created is called tidal locking. Tonight, we are going to explore this beautiful mystery together. We are going to understand why the moon moves the way it does, what forces shaped its motion, and what this ancient dance tells us about the nature of our universe. So settle in, get comfortable, and let the story of the moon carry you gently into the night. To understand tidal locking, we first need to talk about two different kinds of motion. These are the two ways that any object in space can move, and they are often confused with one another. The first kind of motion is called rotation. Rotation is when an object spins on its own axis, like a top spinning on a table, or like the Earth turning through day and night. Right now, as you listen to this, the Earth is rotating. It completes one full spin every 24 hours. That is why we have daytime when we face the sun, and nighttime when we face away. The second kind of motion is called revolution. Revolution is when an object travels around another object following a curved path through space. The Earth revolves around the sun, completing one full lap every 365 days. That is what gives us our year. And the moon revolves around the Earth, completing one full orbit every 27.3 days. These two motions, rotation and revolution, are separate from each other. An object can spin fast while orbiting slowly, or spin slowly while orbiting fast. There is no rule that says they have to match. But here is where things get interesting. For the moon, these two motions are exactly the same. The moon rotates once every 27.3 days, and it also revolves around the Earth once every 27.3 days. This perfect match is called synchronous rotation. The spin is matched to the orbit. And because of this match, the moon keeps the same face pointed toward Earth at all times. Think of it like this. Imagine you are walking in a big circle around a lamp in the center of a room. Now imagine that as you walk, you also slowly turn your body so that you are always facing the lamp. By the time you complete one full lap around the lamp, you have also turned around once. You have rotated once and revolved once. Anyone watching from the lamp would only ever see your face. They would never see your back. This is exactly what the moon does. As it orbits the Earth, it slowly rotates just enough to keep the same side facing us. It is a delicate balance, a perfect coordination between two separate motions, and it did not happen overnight. This synchronization took a very, very long time to develop, billions of years in fact, and the force responsible for creating this match is gravity. Not just any gravity, but a special kind of gravitational effect that we call tidal forces. Now, let us take a moment to understand what gravity really does. We often think of gravity as a simple pull between two objects. The Earth pulls on the moon and the moon pulls on the Earth. This is true, but it is not the whole story. Gravity is not the same everywhere on an object. It is stronger when you are closer to the source and weaker when you are farther away. This might seem like a small detail, but it turns out to be incredibly important. Think about the moon for a moment. The moon is a sphere about 2,000 miles across. The side of the moon that faces the Earth is closer to us by about 2,000 miles than the side that faces away. And because gravity gets weaker with distance, the Earth pulls on the near side of the moon more strongly than it pulls on the far side. This difference in gravitational pull across the body of the moon is what we call a gravitational gradient. And this gradient creates tidal forces. Imagine holding a ball of soft clay in your hands. Now imagine pulling on one side while pushing on the other. The clay would stretch, becoming longer and thinner. That is essentially what tidal forces do to objects in space. They stretch them along the line connecting the two bodies. On Earth, we are very familiar with this effect, even if we do not always realize it. The moon pulls on our planet, and because the side of Earth facing the moon feels a stronger pull than the side facing away, the Earth gets stretched ever so slightly. We see this stretching most clearly in our oceans. The water on the side of Earth closest to the moon is pulled toward the moon, creating a bulge of water, a high tide. At the same time, the water on the far side of Earth, which feels less of the moon's pull, also bulges outward, creating another high tide. This is why many places on Earth experience 2 high tides and 2 low tides each day. The Earth is constantly being stretched by the moon's gravity, and our oceans respond to that stretching. But here is something that might surprise you. The Earth is not the only body being stretched. The moon itself feels the same kind of tidal forces from the Earth. The difference in gravitational pull between the near side and far side of the moon stretches the moon along the line connecting it to Earth. But the moon does not have oceans. It is made of solid rock. So instead of water sloshing around, the rock itself is stretched. The moon has a very slight bulge on the side facing Earth and another slight bulge on the side facing away. These are called tidal bulges, and they are permanent features of the moon frozen into its rocky body. Now we come to the heart of our story. Long ago, when the moon was young, it was spinning much faster than it does today. It rotated quickly on its axis, completing many spins for every orbit around the Earth. And as it spun, those tidal bulges tried to stay pointed toward Earth, because that is where the stretching force was coming from. But because the moon was spinning, the bulges were constantly being carried away from the Earth-facing direction. Imagine a lump of rock on the surface of the moon, part of one of those tidal bulges. As the moon rotates, that lump is carried around, away from the direction of Earth. But the Earth's gravity keeps pulling on it, trying to drag it back toward the Earth-facing position. This creates a kind of tug of war. The moon's rotation tries to carry the bulge away, and the Earth's gravity tries to pull it back. This tug of war has an important effect. The Earth's pull on the bulge creates what is called a torque, a twisting force that tries to slow down the moon's rotation. It is like pressing a brake on a spinning wheel. The Earth was gently, patiently slowing down the moon's spin, one tiny fraction at a time. This braking happened very slowly. The torque was small because the difference in gravity across the moon is small. But gravity never rests. It works constantly, every moment of every day for billions of years. Over time, the moon's rotation slowed down. It spun a little slower, then a little slower still. And as it slowed, something interesting happened. The tidal bulges could stay closer to the Earth-facing direction. They did not get carried as far away by the rotation. And because the bulges were closer to their natural position, the torque, the braking force, became weaker. This process continued for a very long time. The moon kept slowing down and the braking force kept getting weaker until finally the moon reached a special point, a point of balance. At this point, the moon's rotation had slowed down so much that it matched the orbital period exactly. One rotation equaled one orbit. And at this speed, the tidal bulges could stay perfectly aligned with Earth. The near side bulge stayed on the near side. The far side bulge stayed on the far side. There was no more twisting, no more torque, no more braking. The moon had reached its lowest possible energy state. It had become tidally locked to the Earth. This is the state we see today. The moon is locked in synchronous rotation, its spin perfectly matched to its orbit, its tidal bulges permanently facing toward and away from our planet. This lock happened billions of years ago, probably within the first billion years of the moon's existence, and it has remained stable ever since. The moon will continue to show us the same face for as long as it orbits the Earth. Let us pause here and reflect on what we have learned. The moon is not stationary, it is spinning, just as the Earth spins. But its spin is synchronized with its orbit, a perfect match created by the patient work of gravity over billions of years. The tidal forces that stretched the moon also slowed its rotation, draining its energy bit by bit until it settled into a locked position. This is tidal locking, and it is one of the most beautiful examples of how gravity shapes the worlds around us. Now that we understand how the lock was created, let us explore what it means for the moon itself. What are the consequences of this eternal synchronization? What does the moon look like on the side we never see? You have probably heard people talk about the dark side of the moon. This phrase has become famous, inspiring songs and movies and countless conversations about the mysteries of space. But here is an important truth that we need to address. The far side of the moon is not actually dark. It receives just as much sunlight as the side we see. When we look at a full moon, we are seeing the near side fully lit by the sun, and the far side is in shadow. But 2 weeks later, when we see a new moon, the situation is reversed. The near side is in shadow, and the far side is bathed in full sunlight. Over the course of a lunar month, every part of the moon receives equal amounts of day and night. The far side is not the dark side. It is simply the side we cannot see from Earth. It is hidden, not because it lacks light, but because the moon always keeps it turned away from us. The far side is mysterious to us only because of our perspective, not because of any lack of sunshine. And when we finally did see the far side, it was a revelation. In 1959, a Soviet spacecraft called Luna 3 flew around the moon and took the first photographs of the hidden hemisphere. What scientists saw was both familiar and surprising. The far side is covered with craters, just like the near side. But there is a striking difference. The near side has large, dark regions called maria. These are ancient plains of solidified lava, created billions of years ago when the moon was young and volcanically active. We can see them with our naked eyes, forming the patterns we call the man in the moon or the rabbit in the moon, depending on your culture. But the far side has very few of these dark plains. It is almost entirely covered with light-colored, crater-marked highlands. Why this difference? Scientists believe it has to do with the moon's internal structure. The crust on the far side is significantly thicker than the crust on the near side. When asteroids struck the moon billions of years ago, they sometimes cracked through the thinner crust on the near side, allowing molten rock to flow up and fill the impact basins. But on the far side, the thicker crust prevented this from happening. The lava stayed trapped beneath the surface. This difference in crust thickness may itself be related to tidal locking. Some researchers think that the heat from the early Earth warmed the near side of the moon more than the far side, keeping the near side crust thinner and more active for longer. The face that looks toward Earth may have been shaped by that very relationship, by the warmth and gravity of our home planet. There's also a subtle motion that allows us to see a little more than half of the moon's surface over time. This motion is called libration, and it is a gentle wobble in the moon's orientation as seen from Earth. If tidal locking were perfect, we would see exactly 50% of the moon's surface and no more. But the lock is not quite perfect. The moon's orbit is not a perfect circle. It is slightly oval or elliptical. And because of this, the moon moves faster when it is closer to Earth and slower when it is farther away, according to the laws of orbital motion. But the moon's rotation speed stays constant. It spins at the same rate all the time. So when the moon is moving faster in its orbit, the rotation falls slightly behind. We get to peak a little bit around the eastern edge. And when the moon is moving slower in its orbit, the rotation gets slightly ahead. We get to peak around the western edge. This east-west wobble is called libration in longitude, and it allows us to see an extra few degrees of the moon's surface. There is also a north-south wobble caused by the tilt of the moon's axis. The moon's axis is not perfectly perpendicular to its orbit around the Earth. It is tilted by about 6.5 degrees. Because of this tilt, sometimes we can see a little bit over the moon's north pole, and sometimes we can see a little bit under its south pole. This is called libration in latitude. When you combine all of these wobbles together, we can actually see about 59% of the moon's surface over the course of time. Not all at once, but gradually, as the moon rocks gently back and forth in its locked position. It is like watching someone nod and shake their head ever so slightly while still keeping their eyes fixed on you. The attention remains constant, but there is a subtle dance happening around the edges. Libration is a reminder that nothing in the cosmos is perfectly rigid. Even a system that has been locked for billions of years still has room for gentle variation, for subtle shifts and adjustments. The moon is locked, but it is not frozen. It is still responding to the complex gravitational environment around it, still finding its balance in the dance with Earth. Now let us turn our attention back to our own planet, because the story of tidal locking is not just about the moon. The Earth is also affected by this ancient relationship. In fact, the Earth is still being changed by the moon right now as you listen to these words. The same tidal forces that lock the moon are also at work on the Earth itself. Remember those tidal bulges we talked about earlier? The ones in our oceans created by the moon's gravitational pull? Well, the Earth is spinning much faster than the moon orbits. The Earth completes one rotation every 24 hours, but the moon takes about 27 days to orbit once. This means that the tidal bulges, which want to stay aligned with the moon, are constantly being carried ahead by the Earth's faster rotation. The Earth's spin drags the water bulges slightly ahead of the moon's position. And because these bulges are made of actual matter, they have their own gravitational pull. The bulge that is ahead of the moon pulls on the moon, tugging it forward in its orbit. This forward pull gives the moon a little extra energy, which causes it to move into a slightly higher orbit. The moon is slowly drifting away from the Earth. This drift is very slow. The moon moves away from us by about 3.8 centimeters per year, roughly the speed at which your fingernails grow. It seems like nothing, but over millions and billions of years, it adds up. 4 billion years ago, the moon was much closer to the Earth than it is today. It would have appeared much larger in the sky, and the tides would have been much more extreme. And there is another consequence of this process. As the tidal bulges are dragged ahead by Earth's rotation, the moon's gravity pulls back on them, trying to slow them down. This creates a braking effect on the Earth itself, similar to the braking effect that locked the moon. The Earth's rotation is gradually slowing down. Our days are getting longer. This change is also very slow. The Earth's day is getting longer by about 1.4 milliseconds per century. You would never notice it in your lifetime or even in 1,000 lifetimes. But over the vast expanse of geological time, it has made a significant difference. 600 million years ago, when the first complex animals were emerging in the oceans, the Earth was spinning faster. A day was only about 21 hours long. Go back further to the early history of the Earth, and days may have been only 6 hours long. In the distant future, billions of years from now, this process will continue. The Earth will keep slowing down, and the moon will keep drifting away. Eventually, theoretically, the Earth itself could become tidally locked to the moon. This would mean that one side of Earth would always face the moon, and the other side would never see it. A single day on Earth would be as long as a month is today. But this process is so slow that it will take many billions of years, longer than the sun will continue to shine in its current form. We are witnessing a cosmic transformation in slow motion, a gradual exchange of energy between the Earth and the moon that has been happening since the moon was born. The moon gained its lock and became a permanent companion, always showing us the same face. And in return, the moon is slowly stealing the Earth's spin, one tiny fraction at a time, pushing itself further into space as it does so. It is a beautiful and delicate trade, a dance of give and take that will continue for eons. The story of tidal locking does not end with the Earth and the moon. Throughout our solar system and beyond, gravity is performing the same patient work on countless other worlds. Some have already been locked, others are in the process of being locked, and still others have found strange, unexpected rhythms that defy simple categorization. Let us take a journey to some of these other worlds and see what tidal locking looks like elsewhere in the cosmos. At the edge of our solar system, far from the warmth of the sun, there's a pair of objects that have achieved something remarkable. Pluto and its largest moon, Charon, are both tidally locked to each other. This is called a double tidal lock, or mutual tidal locking. Pluto keeps the same face toward Charon, and Charon keeps the same face toward Pluto. They orbit around a common center of gravity, always looking at each other, like two dancers holding hands and spinning together. This mutual lock happened because Charon is unusually large compared to Pluto. Charon is about half the diameter of Pluto and has about 1/8 of its mass. This is a much closer match than the Earth and Moon. Because of this, the tidal forces between Pluto and Charon were strong enough to lock both bodies relatively quickly. Today, if you stood on the near side of Pluto, you would always see Charon hanging in the sky, never moving, never setting. And if you stood on the far side of Pluto, you would never see Charon at all. It would be forever hidden beyond the horizon. Moving closer to the Sun, we find the giant planet Jupiter, surrounded by a family of moons. The 4 largest of these, known as the Galilean moons, were discovered by Galileo over 400 years ago. Their names are Io, Europa, Ganymede, and Callisto. All 4 of these moons are tidally locked to Jupiter, keeping the same face toward the giant planet at all times. But their story is more complicated than simple locking. The 3 inner moons, Io, Europa, and Ganymede, are caught in a special relationship called an orbital resonance. For every orbit that Ganymede completes, Europa completes exactly 2 orbits, and Io completes exactly 4. This precise mathematical relationship is not a coincidence. It is the result of gravitational interactions between the moons over billions of years, pulling them into this synchronized rhythm. This resonance has an important consequence. Even though Io is tidally locked to Jupiter, it is constantly being tugged by Europa and Ganymede. These tugs cause Io's orbit to be slightly elliptical, not perfectly circular. And as Io moves closer and farther from Jupiter in its elliptical orbit, the tidal forces it feels change in strength. Jupiter's gravity squeezes and stretches Io as it orbits, like a ball of dough being kneaded over and over. This constant squeezing generates heat inside Io, a tremendous amount of heat, in fact. Io is the most volcanically active body in the entire solar system. Its surface is covered with hundreds of active volcanoes, spewing sulfur and silicate lava across a tortured landscape. Lakes of molten rock dot the surface. The entire moon is being cooked from the inside by tidal heating. This is a dramatic example of how tidal forces can shape a world, not just locking it in place, but generating enough energy to melt its interior. Europa, the next moon out, also experiences tidal heating. Though less intensely than Io, scientists believe that this heating may be enough to maintain a liquid water ocean beneath Europa's icy surface. This ocean is one of the most exciting places in the solar system to search for life. The combination of liquid water, chemical energy, and tidal warmth creates conditions that might, just possibly, support living organisms. And it is all made possible by the complex dance of tidal locking and orbital resonance. Let us travel now to a world that is not quite locked but not quite free either. Mercury, the smallest planet and the closest to the Sun, was long thought to be tidally locked. For many years, astronomers believed that Mercury kept one face permanently toward the Sun, baking in eternal daylight while the other side froze in eternal night. But when radar observations were made in the 1960s, scientists discovered something surprising. Mercury is rotating, but not in sync with its orbit. Instead, it has settled into a different kind of resonance. Mercury rotates 3 times for every 2 orbits around the Sun. This is called a 3-to-2 spin orbit resonance. It is a near lock, a compromise that the planet reached because of its highly elliptical orbit. The gravitational forces on Mercury change dramatically as it swings closer to and farther from the Sun. A simple 1-to-1 lock, like our moon has with Earth, was not stable for Mercury. But the 3-to-2 rhythm was, and so Mercury settled into this unique pattern. What this means for Mercury is strange and wonderful. If you stood on the surface of Mercury, you would see the Sun rise, move across the sky, stop, reverse direction briefly, then continue on its way and set. At certain points on the surface, you would experience 2 sunrises and 2 sunsets during a single Mercury day. It is a world where the usual rules of day and night are bent into unfamiliar shapes by the power of resonance. Now let us venture beyond our solar system to the planets orbiting other stars. Thousands of exoplanets have been discovered in recent years, and many of them are likely to be tidally locked to their parent stars. This is especially true for planets orbiting red dwarf stars, the most common type of star in our galaxy. Red dwarfs are smaller and cooler than our Sun. Their habitable zones, the regions where liquid water could exist on a planet's surface, are much closer to the star. A planet in this zone would orbit quickly, completing a year in just days or weeks. And because the planet is so close to the star, the tidal forces would be extremely strong. Many scientists believe that most planets in the habitable zones of red dwarfs are tidally locked, always keeping the same face toward their star. What would life be like on such a world? Imagine a planet where one side faces the star forever, bathed in eternal daylight. The surface there would be hot, possibly too hot for life as we know it. The other side would face away from the star forever, trapped in eternal night. That side would be cold, possibly frozen solid. But there is a region in between, a ring around the planet where the star hangs perpetually on the horizon, rising and setting very slowly if at all. This twilight zone might have temperatures suitable for liquid water. It might be the only place on such a planet where life could survive. Scientists have nicknamed some of these worlds eyeball planets because from space they might look like giant eyes. A bright, hot pupil on the day side, a dark, frozen area on the night side, and a ring of potentially habitable territory in between like an iris. These are strange and alien places, very different from our own Earth, where day and night cycle smoothly and every part of the surface sees the sun. Weather on a tidally locked planet would also be unusual. The permanent temperature difference between the day side and night side would drive powerful winds as air heated on the bright side flows toward the cold side. Giant storm systems might form at the boundary, eternal hurricanes marking the edge of light and shadow. Water might evaporate on the day side, travel through the atmosphere, and freeze as snow on the night side, building up massive ice sheets over millions of years. Or perhaps the heat from the star would be distributed more evenly, creating a climate that is strange but livable. We do not yet know if any of these tidally locked exoplanets harbor life. But the very fact that they exist, scattered throughout our galaxy by the billions, tells us something profound about the power of tidal forces. Gravity reaches across space, grabs hold of spinning worlds, and gradually, patiently brings them into lockstep with their stars. It is a universal process, happening right now on countless worlds we have yet to discover. As we contemplate these distant planets, let us also think about the vast stretches of time involved in tidal locking. The moon was locked billions of years ago. Mercury found its resonance over billions of years. The planets around red dwarf stars may have been locked within millions of years of their formation. These timescales are almost impossible for us to grasp. 1,000,000 years is longer than modern humans have existed. 1,000,000,000 years is longer than complex life has existed on Earth. Gravity does not hurry. It does not need to. It has all the time in the universe. Every second of every day for billions upon billions of years, gravity applies its gentle force, slowly shaping the motions of worlds. Stars are born and die. Galaxies collide and merge. And through it all, gravity keeps working, pulling and tugging and twisting, until every spinning object finds its place in the cosmic dance. Think about what this means for the universe as a whole. Given enough time, most moons will become locked to their planets. Most close-in planets will become locked to their stars. Even binary star systems will eventually synchronize their rotations. The universe is gradually settling into states of lower energy, states of balance and harmony. The chaos of the early cosmos, with objects spinning wildly in every direction, is slowly giving way to a more ordered arrangement. This does not happen all at once. It happens one world at a time, one orbit at a time, one tiny adjustment at a time. But it is happening everywhere, all the time. And when we look at the moon tonight and see the same familiar face, we are seeing the result of this cosmic process. We are seeing gravity's patient handiwork, a masterpiece that took billions of years to complete. There is a deep beauty in this process that goes beyond the mechanics of physics. Tidal locking is an example of how simple rules, applied consistently over time, can create complex and elegant outcomes. The law of gravity is simple. Objects with mass attract each other. The strength of the attraction depends on how much mass they have and how far apart they are. That is all there is to it. And yet from this simple rule emerges the intricate choreography of moons and planets, the slow synchronization of spinning worlds, the creation of patterns that will last for billions of years. Think about the moon, as it was 4 billion years ago. It had just been born, probably from a giant collision between the early Earth and another planet-sized object. It was spinning rapidly, completing a rotation in just a few hours. Its surface was molten, glowing with heat. The Earth, too, was young and violent, spinning much faster than it does today. The two bodies were much closer together, with the moon appearing many times larger in the sky than it does now. In those early days, the tidal forces between Earth and moon were enormous. The Earth raised huge tides on the molten surface of the moon, deforming its shape with every rotation. And as we discussed earlier, these tides acted as brakes, slowing the moon's spin. The faster the moon spun, the more the tidal bulges were carried away from the Earth-facing direction, and the stronger the braking force became. It was a rapid process at first, draining the moon's rotational energy quickly. As the moon slowed down, the braking force weakened. The process became more gradual, but it never stopped entirely. Year after year, century after century, millennium after millennium, the moon continued to slow. At some point, probably within the first few 100 million years, the moon's rotation synchronized with its orbit. The lock was achieved, and the moon has been locked ever since, frozen in its orientation, always showing us the same face. But even after the lock was established, the system continued to evolve. The energy that was being drained from the moon's rotation had to go somewhere. It was converted into heat inside the moon, warming its interior, and it was transferred to the moon's orbit, causing the moon to drift slowly outward. This outward drift is still happening today. The moon is still moving away from us, still responding to the transfer of energy that began when it was young. The Earth, too, is still changing. Its rotation is still slowing down, its days still getting longer. The tidal bulges in our oceans are still being dragged ahead by the Earth's spin, and the moon's gravity is still pulling back on them. This friction heats the ocean floors, though not by much. It is a tiny effect, but it is real. The Earth and moon are still in conversation, still exchanging energy, still adjusting their dance. Let us imagine the distant future, millions and billions of years from now. If the system were left undisturbed, what would eventually happen? The Earth's rotation would continue to slow. At some point, the Earth's day would become as long as the moon's orbital period. At that moment, the Earth itself would become tidally locked to the moon. One side of Earth would always face the moon, and the other side would never see it. The tidal exchange would cease, and the system would reach a final equilibrium. But this will not actually happen, at least not completely. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin to expand into a red giant. It will swell to enormous size, possibly engulfing Mercury and Venus and scorching the Earth beyond recognition. Long before the Earth can become tidally locked to the moon, the sun's evolution will transform our entire solar system. The story of the Earth and moon, so ancient and so patient, will eventually come to an end, not because of any failure of the tidal process, but because stars do not live forever. Still, it is remarkable to think about how far the process would go if given the chance. Tidal locking is gravity's way of enforcing order, of bringing chaos into harmony. And given enough time, gravity almost always wins. The universe moves toward states of lower energy, toward configurations that are more stable, more balanced, more synchronized. Tidal locking is just one expression of this universal tendency. Now let us return to the present moment and think about what the moon means to us. For all of human history, the moon has been a constant companion. It has marked our calendars, guided our harvests, and inspired our myths and stories. Ancient people saw faces and figures in its surface, and told tales of gods and rabbits and old men who lived there. Sailors used the moon to navigate. Farmers used it to track the seasons. Lovers have walked beneath its light for as long as there have been lovers. And all this time, the moon has been showing us the same face, the same craters, the same Maria, the same patterns of light and dark. This consistency is not a coincidence. It is the result of tidal locking, a process that began before life existed on Earth and will continue long after we are gone. When we look at the moon, we are seeing the face that gravity chose for us, the side that was destined to look our way ever since the moon found its lock. There is something comforting about this. In a universe that often seems chaotic and unpredictable, the moon is a symbol of constancy. It changes through its phases, growing from new to full and back again, but it always shows us the same features. It rises and sets, moves across the sky, but it never turns away. It is locked to us, bound by gravity, a faithful companion that will remain with us for as long as the Earth and moon exist. Let us now explore some of the finer details of tidal forces and how they work. We have talked about gravitational gradients and tidal bulges, but there is more to say about the physics involved. Understanding these details will give us an even deeper appreciation for the elegance of tidal locking. When we say that gravity is stronger on the near side of an object and weaker on the far side, we are describing what physicists call a tidal field. This field is not uniform. It varies in strength and direction from point to point across the object. If you were to map out the tidal field, you would see a pattern of stretching forces along the line connecting the two bodies and compressing forces perpendicular to that line. Imagine a ball of jelly floating in space, with a massive object like the Earth nearby. The tidal forces from the Earth would stretch the jelly along the line connecting them, making it longer in that direction. At the same time, the jelly would be compressed slightly in the perpendicular directions, making it narrower. The overall shape would change from a sphere to an elongated ellipsoid like a football or an egg. This is exactly what happens to the moon and to the Earth and to any object in a strong enough tidal field. The moon is slightly elongated along the line connecting it to Earth. Its equatorial diameter is about 2 kilometers greater in the direction facing Earth than in the perpendicular direction. This is a small difference compared to the moon's overall size, but it is measurable and it is permanent. The reason the moon's shape is permanent rather than constantly changing is because the moon is tidally locked. The bulge always faces the same direction, toward Earth. If the moon were spinning freely, the bulge would have to continuously reform as different parts of the moon faced Earth. The rock would have to flex and stretch with every rotation. But because the moon is locked, the bulge just sits there, a frozen testament to the tidal forces that shaped it. This is why tidal locking represents a minimum energy state. A freely spinning object in a tidal field is constantly being deformed and undeformed as it rotates. This deformation dissipates energy as heat, but a locked object does not need to deform continuously. Its shape is already aligned with the tidal field and no energy is wasted. Locked objects are more stable, more relaxed, more settled. There is an analogy that might help to make this clearer. Imagine a magnetic compass needle. When you first drop a compass needle into its housing, it might spin and oscillate for a while, swinging back and forth as it settles. But eventually, it stops and points toward magnetic north. Once aligned, the needle is in its lowest energy state, and it stays there. Tidal locking is similar. A spinning moon is like an oscillating compass needle. Tidal forces act like the magnetic field, pulling and tugging until the moon settles into alignment. Of course, the timescales are vastly different. A compass needle settles in seconds. A moon settles in millions or billions of years, but the principle is the same. Systems tend toward their lowest energy states, and they stay there once they arrive. Let us also consider the role of the object's internal structure in tidal locking. Not all objects respond to tidal forces in the same way. A perfectly rigid object with no ability to flex or deform would be much harder to lock. The tidal bulge would be smaller, and the braking torque would be weaker. A more flexible object, on the other hand, would develop larger bulges and lock more quickly. The moon, as it turns out, is not perfectly rigid. It has some internal flexibility, especially in its early history when its interior was hotter and more malleable. This allowed the tidal bulges to develop and the braking torque to take hold. Today, the moon is much cooler and more rigid, but the lock was already established long ago. Objects that are too small to have significant internal structure, like asteroids, generally do not become tidally locked. Their tidal bulges are negligible, and the braking forces are too weak to matter. But larger objects with more mass and more internal structure are susceptible to locking. This is why most large moons in the solar system are tidally locked to their planets, while most small moons and asteroids are not. There is also a factor related to distance. Tidal forces get weaker very quickly as distance increases. In fact, they decrease with the cube of the distance, which means doubling the distance makes the tidal force 8 times weaker. This is why the moon, which is relatively close to Earth, became locked, while the outer planet's most distant moons often are not locked. Distance matters a great deal in the tidal locking game. Let us take a moment to think about what we would see if we could visit the moon in person. Astronauts have walked on the moon, of course. 12 humans set foot on its surface during the Apollo program between 1969 and 1972. They found a world of stark beauty and profound silence. There is no air on the moon, no wind, no weather. Footprints left in the lunar dust will remain undisturbed for millions of years. The sky is black, even during the day, because there is no atmosphere to scatter sunlight. From the surface of the moon, the Earth hangs in the sky like a giant blue marble, slowly going through phases just as the moon does when viewed from Earth. But unlike the moon, which rises and sets as seen from Earth, the Earth appears almost motionless from any given point on the moon's near side. It hovers in the same spot in the sky day after day, only wobbling slightly due to libration. This is a direct consequence of tidal locking. Because the same side of the moon always faces Earth, the Earth appears fixed in the lunar sky. If you travel to the far side of the moon, the Earth would disappear below the horizon and never rise. You would be completely cut off from the sight of your home planet. The far side of the moon is the only place in the Earth-Moon system from which the Earth cannot be seen. It is a lonely place in that sense, isolated from the visual connection to Earth that defines the near side. The Apollo astronauts stayed on the near side, where they could maintain radio contact with Earth. Signals on the far side would be blocked by the moon itself. Future explorers may venture to the far side, perhaps establishing bases in the permanently shadowed craters near the poles, where water ice may be trapped. These missions will help us understand the far side better, filling in the details of a hemisphere that we have only glimpsed from orbit. As we consider the future of lunar exploration, we can also think about the future of the moon itself. The tidal forces that locked the moon are still at work, though their effects are now subtle. The moon is gradually moving away from Earth, as we discussed. In the distant future, the moon will be farther from us than it is today, appearing smaller in the sky. Solar eclipses will eventually become impossible, because the moon will be too far away to completely cover the sun. The moon's influence on Earth's tides will also weaken as it recedes. Our ocean tides will become less dramatic. The braking effect on Earth's rotation will diminish, but these changes will take hundreds of millions of years to become noticeable. For the foreseeable future and for all of human history to come, the moon will remain much as it is now, our faithful companion, our locked partner, our window into the workings of gravity. There is something deeply meditative about thinking on these timescales. Human lives are measured in decades. Civilizations rise and fall over thousands of years. But the moon has been locked for billions of years, and it will remain locked for billions more. We are witnessing just a single moment in an immensely long story, like seeing one frame of a movie that lasts for ages. This perspective can be humbling, but it can also be comforting. The universe operates on its own schedule, indifferent to our hurry and impatience. Gravity does not rush. It does not worry. It simply acts, moment after moment, applying its gentle force until balance is achieved. There is a kind of wisdom in this, a reminder that some things cannot be hurried, that some outcomes require patience measured in geological time. Let us now delve deeper into the phenomenon of tidal heating, which we touched upon when discussing Jupiter's moon Io. This is one of the most dramatic consequences of tidal forces in the solar system, and it illustrates how gravity can generate energy on a massive scale. Tidal heating occurs when an object is caught between competing gravitational influences that prevent it from settling into a perfectly circular orbit. The changing distance from the primary body causes the tidal forces to fluctuate, continuously squeezing and stretching the object's interior. This flexing generates friction, and friction generates heat. On Io, the heat is so intense that it melts the moon's interior and drives continuous volcanic activity. Hundreds of volcanic vents cover the surface, erupting plumes of sulfur and silicate lava that can reach hundreds of kilometers into space. The entire surface of Io is reshaped by these eruptions on a timescale of just a few thousand years. Ancient craters are buried beneath fresh lava flows. The landscape is constantly renewing itself, painted in shades of yellow, orange, red, and black by the sulfur compounds that dominate its chemistry. This makes Io the most volcanically active body in the entire solar system, more active than Earth by a wide margin. And yet Io is tidally locked to Jupiter. It always shows the same face to the giant planet, just as our moon shows the same face to Earth. The lock does not prevent the heating, because the heating is caused by the elliptical orbit, not by the rotation. Io is locked, but it is also being kneaded like dough by the changing tidal forces as it moves closer to and farther from Jupiter. Europa, the next moon outward from Jupiter, experiences less intense tidal heating than Io, but the heat is still significant. Beneath Europa's icy surface, which is covered with a cracked and fractured crust of water ice, scientists believe there is a liquid water ocean. This ocean may contain more water than all of Earth's oceans combined, and it is kept liquid by the heat generated from tidal flexing. The possibility of life in Europa's ocean is one of the most exciting prospects in modern astrobiology. Life on Earth arose in the oceans and thrived around hydrothermal vents on the ocean floor, where hot water rich in chemicals bubbles up from the interior. If similar vents exist on Europa, they could provide the energy and nutrients needed to support life. We do not know if life exists there, but the conditions seem promising and future missions may one day investigate. Ganymede, the largest moon in the solar system, is also tidally locked to Jupiter and also participates in the orbital resonance with Io and Europa. Its tidal heating is less intense than its inner neighbors but still present. Ganymede has a thin magnetic field, the only moon known to have one, which may be related to a liquid iron core kept warm by residual heat from formation and possibly supplemented by tidal heating. Callisto, the outermost of the 4 Galilean moons, is not part of the orbital resonance. Its orbit is nearly circular, and it experiences minimal tidal heating. As a result, Callisto is a more ancient, heavily cratered world, with a surface that has not been renewed by geological activity in billions of years. It is a frozen time capsule, preserving the record of impacts from the early solar system. The contrast between Io and Callisto is striking. Both are tidally locked to Jupiter. Both are roughly the same size. But one is a violent volcanic hellscape, while the other is a cold, dead world. The difference is the orbital resonance that keeps Io's orbit elliptical and pumps heat into its interior. Tidal locking alone does not determine a moon's fate. The orbital environment matters just as much. Let us turn now to think more about the exoplanets orbiting distant stars, and what tidal locking might mean for their potential to host life. As we mentioned earlier, many planets in the habitable zones of red dwarf stars are likely to be tidally locked. These red dwarfs are the most common type of star in the galaxy, and they are also the longest lived. While our sun will burn for about 10 billion years, a red dwarf can shine for trillions of years. This gives life an extraordinarily long time to develop on any habitable planets. But the tidal locking presents challenges. A planet that always keeps one face toward its star will have extreme temperature differences between the day side and night side. The day side could be hundreds of degrees hotter than the night side. Water on the day side might evaporate entirely and freeze permanently on the night side, potentially leaving the planet dry and lifeless. However, recent studies have suggested that the situation may not be as dire as it first seems. If the planet has a thick atmosphere, heat can be transported from the day side to the night side by powerful winds. This would moderate the temperature extremes, creating a more habitable environment in the twilight zone and possibly across much of the surface. Oceans, too, can help distribute heat. Water absorbs and retains heat better than land, and ocean currents can carry warm water from the day side to the night side. A tidally locked ocean world might be surprisingly habitable, with a warm, mild climate over much of its surface. The clouds that form on such a planet could also play a role. Reflective clouds on the day side would bounce some of the starlight back into space, cooling the surface. Clouds on the night side might help trap heat, preventing it from escaping. The interplay of clouds, winds, and ocean currents creates a complex climate system that is difficult to predict without detailed modeling. Some scientists have speculated about what life might look like on a tidally locked world. Plants, if they existed, would always face the same star, with no need to track the sun across the sky. They might have evolved to be permanently oriented toward the light source, with large, flat leaves to capture as much energy as possible. Animals might migrate between the warmer and cooler regions, following the temperature gradient like Earth animals follow the seasons. Or they might live permanently in the twilight zone, adapted to the eternal half-light. The ecology of such a world would be profoundly different from anything we know on Earth. We do not yet have the technology to observe these details on exoplanets. Current telescopes can detect the presence of atmospheres and measure their basic composition, but they cannot see surface features or weather patterns. Future telescopes, such as those planned for the coming decades, may be able to study the atmospheres of tidally locked worlds in more detail, searching for signs of habitability and perhaps even life. The search for life beyond Earth is one of the great scientific quests of our time. Tidal locking is a key factor in this search because it shapes the environments of so many potentially habitable worlds. Understanding how tidal forces affect planetary climates is essential to understanding where life might exist in the universe. As we think about these distant worlds, let us also reflect on the nature of gravity itself. Gravity is one of the four fundamental forces of nature, along with electromagnetism, the strong nuclear force, and the weak nuclear force. Of these four, gravity is by far the weakest. The electromagnetic force that holds atoms together is about 10 to the power of 36 times stronger than gravity. The strong force that holds atomic nuclei together is even stronger. And yet gravity dominates the universe on large scales. This is because gravity is always attractive, never repulsive, and because its range is infinite. The other forces either cancel out at large scales because they have both positive and negative charges, or they fade quickly with distance. Gravity, weak as it is, just keeps adding up. Every bit of mass in the universe attracts every other bit of mass. Over cosmic distances, this adds up to enormous effects. Gravity shapes the structure of the universe. It pulls gas and dust together to form stars. It holds stars together in galaxies. It binds galaxies together in clusters. And on smaller scales, it locks moons to planets and slows the rotation of worlds. Over billions of years, the same force that keeps your feet on the ground keeps the moon showing us the same face forever. There's a profound unity in this. The same laws of physics that govern the fall of an apple govern the motion of galaxies. The universe is consistent. It follows rules. And by studying these rules, we can understand phenomena as different as tidal locking on the moon and the formation of supermassive black holes at the centers of galaxies. Einstein showed that gravity is not really a force in the traditional sense, but a curvature of space and time caused by the presence of mass. Objects move along curved paths because space itself is curved by the mass around them. The moon is not so much pulled toward the Earth as it is rolling along the curved space that the Earth creates. This is the essence of general relativity, one of the most beautiful and successful theories in all of physics. From this perspective, tidal locking is an expression of the geometry of space-time. The moon settles into a locked rotation because this is the configuration that follows most naturally from the curved space-time around the Earth. It is the path of least resistance, the shape that the system falls into when given enough time. Gravity is not pushing or pulling so much as guiding, like water finding its way downhill. This geometric view of gravity opens up even more wonders. Black holes, which are regions of space-time so curved that nothing can escape, not even light, exhibit extreme tidal forces. An object falling into a black hole would be stretched along the direction of fall and compressed perpendicular to it, a process colorfully known as spaghettification. The tidal forces near a black hole can be strong enough to tear stars apart. In fact, astronomers have observed stars being disrupted by supermassive black holes at the centers of distant galaxies. These events, called tidal disruption events, produce brilliant flares of light as the stellar material is heated and consumed. It is tidal force writ large, the same gentle stretching that shaped our moon, amplified to cosmic extremes. But let us return to our quiet moon hanging in the night sky, showing us its familiar face. The moon knows nothing of black holes and galaxy clusters. It simply orbits, locked in place, a testament to the patience of gravity. It has been doing this for longer than complex life has existed on Earth. It will continue doing this for longer than anyone can imagine. And in this constancy, there is peace. The moon does not struggle against its lock. It does not try to spin free. It rests in equilibrium, perfectly balanced between the forces acting upon it. This is the natural state of things, the state toward which all systems tend given enough time. Chaos gives way to order. Motion gives way to stillness. The dance continues, but the steps have become so familiar that they seem effortless. As you settle into sleep tonight, let this thought drift through your mind. The universe is full of motion and change, but it is also full of stability and harmony. The moon has found its place. The Earth has found its partner. Together, they orbit the sun, and the sun orbits the center of the galaxy, and the galaxy drifts through the cosmic web. Everything is connected, everything is held together by the same invisible threads of gravity. And in this vast, interconnected cosmos, you are here, on this small planet, looking up at the same moon that has looked down on every human who ever lived. The same face, the same craters, the same silent gaze. Tidal locking has given you this gift, this constant companion in the night sky. It is a connection that spans billions of years, a relationship forged by gravity and time. Let this thought be a comfort as you drift toward sleep. The universe is large, but it is not indifferent. It is organized, structured, shaped by forces that create beauty and order. The moon's locked face is just one example of this cosmic artistry. There are countless others scattered across the sky, waiting to be discovered, but for now it is enough to rest, to let the gentle rhythm of the night wash over you, to know that the moon is there, steady and unchanging, watching over you as it has watched over countless generations before. The dance of gravity continues, silent and eternal, and you are part of it here, on this pale blue dot under the watchful eye of a locked and ancient moon. Let us now journey back in time, billions of years, to when the moon was young and the solar system was still a violent, chaotic place. Understanding how the moon formed helps us appreciate the journey it has taken to become the locked companion we know today. The leading theory for the moon's origin is called the giant impact hypothesis. About 4.5 billion years ago, when the Earth was still young and molten, a massive object the size of Mars struck our planet. This object has been given the name Theia, after the Greek goddess, who was the mother of the moon goddess Selene. The collision was catastrophic. Both bodies were partially vaporized by the impact, sending a vast cloud of debris into orbit around the Earth. Within this ring of debris, gravity began its work. Small particles stuck together, forming larger clumps. These clumps attracted more material, growing steadily. Within a surprisingly short time, perhaps just a few years or decades, the moon coalesced from this orbiting cloud. It formed much closer to Earth than it is today, perhaps only about 15,000 miles away compared to the nearly 240,000 miles that separate us now. The early moon was very different from the serene silver orb we see tonight. It was molten, covered in a global ocean of liquid rock called a magma ocean. The heat from its formation kept it glowing, a second, smaller sun in the Earth's sky. And it was spinning rapidly, completing a rotation in just a few hours. The tidal bulges on this molten moon were large and easily deformed. The Earth, too, was molten and spinning fast. Days may have been only 4 to 6 hours long. The two bodies were locked in a violent gravitational embrace, raising enormous tides on each other. But even in this chaos, the forces of tidal locking were already at work. The spinning moon's tidal bulges were being dragged away from the Earth-facing position, and the Earth's gravity was pulling them back, creating the torque that would slowly, inexorably slow the moon's rotation. Because the moon was so close and its interior was so fluid, the initial locking happened relatively quickly in geological terms. Within a few tens of millions of years, perhaps 100 million at most, the moon's rotation had synchronized with its orbit. The lock was established while the moon was still warm, perhaps even while parts of its surface were still liquid. And then, as the moon cooled and solidified, the lock became permanent. Meanwhile, the moon was also moving away from Earth. The tidal exchange of energy was pushing it into a higher orbit, inch by inch, year by year. As the moon moved farther away, its orbital period increased, and so did its rotation period, maintaining the lock. The two motions stayed synchronized, always matching, always in step. The early Earth experienced dramatic tides during this period. With the moon so much closer, the tidal forces were enormously stronger than they are today. Tides may have risen and fallen by hundreds of feet, flooding and draining coastal areas in a rhythm much faster than our current 24-hour cycle. Some scientists believe these intense tides may have played a role in the origin of life on Earth, stirring the oceans and concentrating chemicals in ways that could have helped the first simple organisms form. As millions and billions of years passed, the moon continued to recede and the Earth continued to slow. The tides became gentler, days became longer. The moon shrank in the sky, becoming smaller and smaller as seen from Earth's surface. The violent, close relationship of the early days gave way to the quieter, more distant partnership we have today. This history is written in the rocks and in the mathematics of orbital mechanics. By studying the layers of ancient sediments, scientists can sometimes find evidence of the tidal rhythms of the distant past. By modeling the gravitational interactions between Earth and Moon, they can trace the Moon's orbital evolution backward in time. All the evidence points to the same story: a violent birth, a rapid lock, a slow separation, and the calm, synchronized dance we see today. The story of tidal locking is not just about the past. It continues into the present, and it will continue into the future. Right now, as you listen to these words, the moon is still moving away from Earth. It is receding at about 3.8 centimeters per year, roughly the width of a few fingers. This is a slow process, imperceptible to human senses, but it is measurable by the precise laser-ranging experiments that have been ongoing since the Apollo astronauts left reflectors on the lunar surface. Scientists bounce laser beams off these reflectors and measure the time it takes for the light to return. By tracking these measurements over decades, they have confirmed the moon's gradual recession with extraordinary precision. This is science in action, using technology to measure the very slow motions of worlds. In the distant future, the recession will continue. 1 billion years from now, the moon will be farther away, appearing smaller in the sky. Solar eclipses will become less common because the moon's apparent size will no longer perfectly match the sun's. Eventually, total solar eclipses will become impossible, replaced by annular eclipses where a ring of sunlight remains visible around the moon's silhouette. The Earth's rotation will also continue to slow. Days will become longer, creeping toward the eventual theoretical equilibrium where the Earth itself is locked to the moon. But as we discussed earlier, this complete mutual lock will probably never be achieved, because the sun's evolution will transform the system first. Still, the trend is clear. Gravity is patient. It works slowly, but it works continuously. Given enough time, it brings rotating bodies into synchronization and pushes orbiting bodies apart. The universe is gradually winding down, settling into states of lower energy and greater stability. Tidal locking is one manifestation of this cosmic relaxation. Now let us expand our view and consider some additional examples of tidal locking throughout the solar system, beyond those we have already discussed. Almost every large moon in the solar system is tidally locked to its planet. This is not a coincidence. It is a reflection of the ubiquity of tidal forces and the effectiveness of the locking process. Saturn, the ring giant, has a beautiful collection of moons. Its largest moon, Titan, is tidally locked. Titan is unique in the solar system for having a thick, dense atmosphere, richer than Earth's in some ways. It has lakes and seas of liquid methane and ethane, and rain falls from its hazy orange skies. Despite all this activity, Titan always keeps the same face toward Saturn. The tidal lock does not prevent atmospheric circulation or surface geology. It simply means that the moon's rotation is synchronized with its orbit. Enceladus, one of Saturn's smaller moons, is also tidally locked. This icy world has become famous for the jets of water vapor and ice particles that erupt from cracks near its south pole. These jets are powered by tidal heating. Enceladus has a subsurface ocean, kept liquid by the heat generated from its slightly elliptical orbit around Saturn. Like Europa around Jupiter, Enceladus is a candidate for harboring life in its hidden waters. And like Europa, it is tidally locked to its planet. Uranus and Neptune, the ice giants in the outer solar system, also have tidally locked moons. Uranus's largest moons, including Titania, Oberon, Umbriel, Ariel, and Miranda, are all locked. Neptune's largest moon, Triton, is locked as well. Triton is an unusual moon because it orbits Neptune backward, in the opposite direction to Neptune's rotation. Scientists believe Triton was captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Despite its backward orbit, Triton is locked always, showing the same face to Neptune. Even dwarf planets have locked moons. Pluto and Charon, as we discussed, are mutually locked, but Pluto also has several smaller moons, including Nix and Hydra, which tumble chaotically rather than being locked. These small moons are too far from Pluto and too small for the tidal forces to have synchronized their rotations. They spin freely, showing different faces to Pluto and Charon as they orbit. This contrast between locked and unlocked moons illustrates an important point. Tidal locking is not inevitable. It requires certain conditions. The object must be close enough to the primary body for the tidal forces to be significant. It must be large enough to have a meaningful internal structure that can develop tidal bulges, and enough time must have passed for the breaking process to complete. If any of these conditions is not met, the object remains unlocked. The moons of Mars, Phobos and Deimos, are both tidally locked to Mars. Phobos, the larger and closer of the two, is also spiraling inward toward Mars, the opposite of what is happening with our moon. In the distant future, Phobos will either crash into Mars or be torn apart by tidal forces to form a ring around the planet. This is an example of how tidal forces can lead to orbital decay when certain conditions are met. Phobos orbits Mars faster than Mars rotates. This means the tidal bulge on Mars is carried behind Phobos's position, not ahead of it. The gravitational interaction drags Phobos backward, slowing it down and causing it to spiral inward. It is the reverse of the situation with our moon, which orbits more slowly than the Earth rotates. Our moon is pushed outward while Phobos is pulled inward. Same physics, different outcome depending on the relationship between orbital and rotational periods. As we survey the solar system, we see that tidal locking is the rule, not the exception, for large moons close to their planets. This tells us that the process is efficient and that gravitational forces have had billions of years to operate. The calm, synchronized rotations we see today are the end product of a long history of deformation and breaking. Every locked moon has its own story, its own journey from rapid spin to quiet synchronization. Let us also briefly consider the rotation of planets themselves. Planets are much farther from their stars than moons are from their planets, and so tidal forces from the star are weaker. The giant planets, Jupiter, Saturn, Uranus, and Neptune all spin rapidly, with days measured in hours rather than Earth days. They are too far from the Sun for solar tides to have significantly slowed their rotation. The terrestrial planets, Mercury, Venus, Earth, and Mars, have more varied rotational states. Mercury, as we discussed, is in a 3:2 resonance with the Sun, a near lock caused by its eccentric orbit. Venus rotates extremely slowly, taking 243 Earth days to complete one rotation longer than its year. Venus also rotates backward, with its north pole pointing down relative to its orbit. The reason for this unusual state is not fully understood, but it may involve a combination of tidal effects, atmospheric dynamics, and ancient impacts. Earth rotates once every 24 hours, as we know, and is slowly slowing down due to lunar tides. Mars rotates at nearly the same rate as Earth, with a day just over 24 hours long. Mars's moons are too small to have significant tidal effects on Mars's rotation, so its spin is largely primordial, a remnant of its formation. Tidal locking, then, is primarily a phenomenon of close-in moons and very close-in planets. Planets in the habitable zones of Sun-like stars are generally too far for tidal locking. But planets in the habitable zones of red dwarfs are close enough to be locked. This makes tidal locking a key factor in the habitability of planets around the most common type of star in the galaxy. As we think about these varied worlds, each shaped by gravity in its own way, we are reminded of the diversity of the cosmos. No two moons are exactly alike. No two planets have identical histories. And yet the same physical laws govern them all. Gravity pulls, tides stretch, rotation slows. These simple principles, applied across billions of years and countless worlds, produce the rich tapestry of motions and configurations we observe today. And in the midst of this tapestry, there is our moon, our particular moon, with its particular face, locked in its particular dance with our particular planet. It is one example among many, but it is the example that matters most to us. It is the moon that lights our nights, guides our tides, and has inspired our stories since the beginning of human memory. Let us take a moment to appreciate this simple fact. Of all the locked moons in the universe, we live beside this one. Of all the faces it could show, it shows us this one. The dark seas of basalt and the bright highlands, the ancient craters named for scientists and explorers, the subtle patterns that different cultures have seen as different figures. This is our moon, our companion, our partner in the cosmic dance. As night settles deeper and the stars grow brighter, let us continue our journey through the gentle mysteries of tidal locking. We have explored the physics and the history, the moons and the planets. Now let us take a more contemplative path, reflecting on what this phenomenon tells us about the nature of our universe. There is a principle in physics called the principle of least action. It states that physical systems tend to evolve in ways that minimize a certain quantity called action, which is related to energy. Systems seek out paths and configurations that are in some sense the most efficient, the most economical, the most natural. A ball rolling down a hill takes the steepest path. Light traveling through different materials bends in a way that minimizes travel time. And rotating bodies in a tidal field settle into locked configurations that minimize the energy dissipated by deformation. Tidal locking is an expression of this deep principle. The moon is not locked because of any special circumstance or accident. It is locked because that is the lowest energy state available to it, given the constraints of its orbit and the presence of Earth's gravity. It is locked because the universe favors stability, favors balance, favors configurations where energy is not wasted. This does not mean the universe is conscious or purposeful. The laws of physics are not goals or intentions. They are simply descriptions of how things behave. But there is a kind of elegance in these laws, a mathematical beauty that has captivated physicists and philosophers for centuries. The fact that the universe operates according to principles like least action, that it tends toward equilibrium and stability, suggests a deep order underlying the apparent chaos. Consider how the moon's lock was achieved. Billions of years of gentle, patient braking. Countless rotations, each slightly slower than the last. The gradual alignment of tidal bulges with the Earth-facing direction. And finally, the settling into synchronization, the achievement of perfect balance. There was no sudden moment of locking, no click or snap. Just a smooth, continuous approach to equilibrium, like a pendulum slowly coming to rest. This gradual approach is characteristic of many natural processes. Rivers carve canyons grain by grain. Mountains rise millimeter by millimeter. Stars fuse hydrogen atom by atom. The universe often works through the accumulation of tiny effects over vast times, achieving outcomes that seem miraculous when viewed from a human perspective, but are simply the natural result of consistent, patient processes. And so it is with tidal locking. The moon did not suddenly stop spinning and face the Earth. It slowed gradually, imperceptibly, over timescales longer than any human civilization. The lock was achieved through the steady, unrelenting work of gravity, operating every moment of every day for billions of years. When we look at the locked moon tonight, we are seeing the product of this immense labor, this cosmic patience. Let us think about what the lock means for the moon as a world. The near side and the far side have had very different histories, shaped in part by the lock itself. The near side, always facing Earth, has been bathed in the light of our planet for billions of years. During the moon's early molten phase, the warmth of the nearby Earth may have kept the near side crust thinner and more geologically active. The volcanic eruptions that created the Maria were concentrated on the near side, filling the ancient impact basins with dark basalt. The far side, always facing away, was colder and more isolated. Its crust grew thicker. When impacts occurred, the lava did not rise to fill them. The far side remains heavily cratered, its ancient surface largely unchanged since the period of heavy bombardment over 4 billion years ago. It is like a museum of the early solar system, preserving the scars of ancient collisions. The asymmetry between the two sides is not just superficial, it extends deep into the moon's interior. The center of mass of the moon is not exactly at its geometric center. It is shifted slightly toward the Earth. This means the near side is, on average, made of denser material than the far side. The tidal lock has frozen this asymmetry in place, ensuring that the denser side always faces us. Some scientists have proposed that this asymmetry itself played a role in the locking process. If one side of the moon was denser than the other, even slightly, then that side would be preferentially pulled toward the Earth by gravity. The lock would naturally occur with the denser side facing inward. The moon found its balance like a weighted die that always lands with the heavy side down. Whether this asymmetry was the cause or the consequence of the lock is still debated. The history of the moon is complex and many factors may have contributed. But the end result is clear. The moon is locked with its near side facing Earth, and this configuration has been stable for billions of years. Let us also consider the psychological and cultural impact of the locked moon. Throughout human history, people have looked up at the same face and seen patterns. In Western culture, the pattern is often called the man in the moon. In East Asian cultures, it is sometimes seen as a rabbit pounding rice or medicine. In South America and other regions, different figures have been identified. These patterns are not real, of course. They are the result of our brains seeking familiar shapes and random arrangements of light and dark. But the fact that everyone sees the same patterns is a direct consequence of tidal locking. If the moon rotated freely, showing us different faces on different nights, these cultural patterns would not have developed in the same way. The moon would have been a more dynamic, changing presence in the sky with no fixed features to identify. Instead, the lock gave us a constant companion, a face that could be studied and named and remembered. The moon became a personality, a character in our stories because it always showed us the same features. This constancy has also been important for science. Early astronomers could map the moon in detail because its features never changed position. They gave names to the craters and seas, names like Tycho and Copernicus and Oceanus Procellarum. They tracked the librations and predicted the phases. They used the moon as a laboratory for understanding other worlds. When humans finally traveled to the moon in the 1960s and 70s, they landed on familiar territory. The landing sites had been studied for years through telescopes. The astronauts knew what features to expect, what terrains to navigate. The lock made the moon accessible in a way that a freely rotating body would not have been. Now let us shift our attention to the broader cosmos and think about what tidal locking means for the search for extraterrestrial life. As we have discussed, many planets in the habitable zones of red dwarf stars are likely to be tidally locked. This has led some scientists to wonder whether such worlds could support complex life, or whether the extreme conditions of permanent day and permanent night would make life impossible. The answer is not yet known. Computer models suggest that atmospheres and oceans can distribute heat effectively, moderating the temperature extremes. The twilight zone between the day side and night side might be habitable over large areas. Life, if it exists on such worlds, might cluster in this region, following the boundary between light and darkness. But there are other challenges. Tidally locked planets around red dwarfs might be subject to intense stellar flares, which could strip away atmospheres and sterilize surfaces. The lack of a day-night cycle might affect biological rhythms in ways we cannot predict. The physics of tidal locking is well understood, but the biology is still largely speculative. What we do know is that tidal locking is common in the universe. Most planets close to their stars will be locked. If life is common, then life on locked worlds might also be common. The strange, asymmetric environments created by tidal locking might be the norm, not the exception, for habitable planets in the galaxy. This is a humbling thought. We live on a planet with a comfortable day-night cycle, with moderate tides, with a moon that is gradually receding rather than hovering overhead. Our situation may be unusual. The typical habitable world may look very different, with a star fixed in the sky with eternal light on one side and eternal darkness on the other. If we ever encounter life elsewhere in the universe, it may have evolved under conditions very unlike our own. Let us now return once more to the moon and think about its future. We have discussed how the moon is moving away from Earth and how the Earth's rotation is slowing down. These trends will continue for billions of years. The moon will become smaller in the sky, solar eclipses will change in character, the tides will become weaker. But there are also more dramatic possibilities. In about 50 million years, the moon may no longer be able to completely cover the sun during an eclipse. Total solar eclipses, which have inspired awe and wonder throughout human history, will become impossible. Future generations, if any exist, will never experience the strange twilight darkness of totality, the corona glowing around the silhouette of the moon. This is a reminder that even stable systems change over time. The Earth-Moon system has been relatively constant throughout human history, but it is not eternal. Everything evolves, everything changes. The lock remains, but the parameters of the lock shift slowly, imperceptibly over geological time. And on even longer timescales, more dramatic changes await. If the Earth and Moon were left alone, without the complicating factor of the sun's evolution, they would eventually reach a mutual tidal lock. The Earth would slow down until one of its days equaled one lunar month. At that point, the Earth and Moon would be locked together, always facing each other like Pluto and Charon. The tides would cease. The moon would hang motionless in the sky over a single point on Earth, never rising or setting, but this will never happen because the sun will run out of fuel first. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin to swell into a red giant. Its outer layers will expand, possibly engulfing the inner planets. The Earth will be scorched, its oceans boiled away, its atmosphere stripped into space. The moon will be baked as well, its surface transformed by the intense heat. Eventually, the sun will shed its outer layers and collapse into a white dwarf, a small, hot remnant of its former self. The Earth and Moon, if they survive, will orbit this dim ember, frozen and silent. The tidal lock will still be in place, but there will be no one to observe it. The face of the moon will still look toward Earth, but Earth will be a dead world, a monument to a vanished biosphere. This is the ultimate fate of all planetary systems. Stars die, planets cool. The patient work of gravity continues, but eventually there is nothing left to shape. The universe winds down, entropy increases, and the delicate structures we call worlds and moons dissolve into the cosmic background. But that is a story for another time, a story of the far future. Tonight we are here in the present, under a living moon orbiting a living Earth. The sun still shines, the tides still rise and fall, life flourishes in the oceans and on the land, and the moon shows us its familiar face, unchanged since our ancestors first looked up in wonder. Let this be the image you carry into sleep, not the distant future of dead stars and frozen worlds, but the present moment of beauty and connection. The moon is there, right now, locked in its eternal gaze. The same face that Shakespeare saw, that Galileo studied, that the Apollo astronauts walked upon. It is your moon, our moon, humanity's moon. And as you drift towards sleep, let the gentle rhythm of the tides echo in your mind. The rise and fall, the push and pull, the endless dance of gravity between Earth and Moon. This dance has been going on for billions of years and will continue for billions more. You are part of it. Every cell in your body contains atoms forged in ancient stars. Every breath you take is part of the great cycle of matter and energy that connects you to the cosmos. The moon is locked, the dance continues, and somewhere on a small planet orbiting an ordinary star, a conscious being contemplates the mystery and drifts peacefully to sleep. Before we bring our journey to a close, let us linger a while longer in the quiet contemplation of gravity and time. There are still more wonders to explore, more gentle mysteries to unfold. The universe is vast, and even a single topic like tidal locking opens doors to countless other marvels. Consider for a moment the sheer improbability of your existence. You are here, on this planet, at this moment in cosmic history, able to think about the moon and its locked rotation. The atoms that make up your body were forged in the hearts of dying stars billions of years ago. They drifted through space, coalesced into planets, cycled through rocks and oceans and living things for eons before coming together to form you. And now those atoms are arranged in such a way that they can contemplate their own history, can wonder about the dance of gravity, can feel a sense of awe at the beauty of the cosmos. This is not something to take for granted. Most of the universe is empty space, cold and dark and lifeless. Stars burn for billions of years, but very few of them have planets where life could thrive. And even on planets where life does emerge, intelligence and consciousness are rare and precious outcomes. You are a unique arrangement of matter, a brief flash of awareness in the vast cosmic night. And you are using that awareness to think about the moon, to understand tidal locking, to appreciate the patient work of gravity over billions of years. There is something deeply moving about this. The universe has no obligation to be comprehensible. It has no requirement to produce beings who can understand it. And yet here we are, looking up at the moon, tracing the paths of its motion, unraveling the secrets of its locked rotation. We are the universe becoming aware of itself, the cosmos looking back at its own reflection. This perspective can bring a sense of peace. Whatever challenges you face in your daily life, whatever worries keep you awake at night, you are part of something much larger. You are connected to the moon, to the stars, to the vast web of gravity that holds the universe together. You are not separate from the cosmos. You are an expression of it, a temporary eddy in the river of matter and energy that flows through all things. And the moon is there to remind you of this connection. Every night it rises and sets, goes through its phases, shows you its familiar face. It is a constant in a world of change, a symbol of stability and continuity. The same craters that ancient peoples named are still there. The same light that guided travelers across deserts and oceans still shines. The moon is old, far older than any human civilization, and it will endure long after we are gone. But for now, it is here, and we are here, sharing this moment together. Let us think once more about the physics of tidal locking, approaching it from a slightly different angle. We have talked about gravitational gradients and tidal bulges, about torque and braking and equilibrium. Now let us consider the energy involved. When the moon was spinning rapidly and the Earth was raising tides on it, energy was being transferred from the moon's rotation to its orbit and to heat. The rotational kinetic energy, the energy of the spin, was being drained away. Some of it went into slightly increasing the moon's orbital energy, pushing it to a higher orbit. Some of it was dissipated as heat inside the moon, warming its interior. This transfer of energy follows the laws of thermodynamics. Energy cannot be created or destroyed, only transformed from one form to another. The moon's rotational energy was converted to orbital energy and thermal energy. The total energy of the system was conserved, but its distribution changed. Once the lock was established, the energy transfer largely ceased. A locked moon does not need to continuously deform as it rotates, so there is no friction to generate heat. The small residual tidal heating from librations is negligible. The system has reached a state where very little energy is being exchanged between the rotation and the orbit. This is why the lock is stable. It is an energy minimum, a configuration that the system settles into and remains in. The same principle applies to all tidally locked bodies. They have reached their minimum energy configurations, their most stable states. Gravity has done its work, draining the excess rotational energy and distributing it elsewhere. The locked rotation is not imposed from outside, it is an emergent property of the system, arising naturally from the interactions of mass and gravity over time. This is one of the beautiful things about physics. Complex behaviors emerge from simple rules. The law of gravity is simple. The laws of thermodynamics are simple. But from these simple rules, the entire diversity of locked and unlocked rotations, of orbital resonances and tidal heating, of rising and falling moons and planets emerges. The universe is a vast symphony, and the simple physical laws are the notes from which the music is composed. Now let us consider the cultural and spiritual significance of the moon across different human societies. Throughout history, the moon has been associated with gods and goddesses, with fertility and harvest, with mystery and romance. Its phases have been used to mark time, to schedule rituals, to plan agricultural activities. The moon has been worshipped, feared, celebrated, and studied by every human culture we know of. In ancient Mesopotamia, the moon god Sin was one of the most important deities. In ancient Egypt, the moon was associated with Thoth, the god of wisdom and writing. In Greek mythology, the moon was personified as Selene, a goddess who drove a chariot across the night sky. In many cultures, the moon was seen as feminine, complementing the masculine sun, representing cycles of birth and death, of waxing and waning. These associations were not arbitrary. They grew out of the moon's observable behavior. Its regular phases, repeating every month, made it a natural symbol of cycles and renewal. Its gentle light, so different from the harsh brightness of the sun, gave it a softer, more mysterious quality. And its constant face, always showing the same patterns, made it a familiar presence, a friend in the darkness. Tidal locking made all of this possible. If the moon rotated freely, showing different faces each night, the patterns would be less recognizable, the cultural associations weaker. The man in the moon, the rabbit in the moon, the countless other figures that different cultures have seen all depend on the lock. Gravity shaped not only the moon's rotation, but also human culture, giving us a constant companion that we could name and story and love. Even today, the moon retains its power over our imagination. Astronauts describe the profound experience of seeing Earth from the lunar surface, a pale blue dot hanging in the black sky. Artists continue to paint the moon, poets to write about it, musicians to sing of it. Science has explained the moon's motion and composition, but it has not diminished the moon's beauty or mystery. If anything, understanding the physics of tidal locking makes the moon more wondrous, not less. The moon is a bridge between science and poetry, between fact and feeling. It is something we can study with telescopes and mathematics, and also something we can admire and wonder at with the simplest human emotions. This dual nature, this ability to be both a scientific object and a source of beauty, is one of the great gifts of astronomy. The universe is not only intelligible, it is also magnificent. As we approach the end of our journey, let us gather together the threads of our exploration. We began with a simple question. Why does the moon always show us the same face? The answer took us through the physics of gravity and tides, through the history of the moon's formation and locking, through the consequences for the moon's surface and for the Earth's rotation. We traveled to other worlds, to Pluto and Charon with their mutual lock, to Jupiter's moons with their volcanic heating and hidden oceans, to Mercury with its near-lock resonance, to distant exoplanets orbiting red dwarf stars. We saw that tidal locking is not a curiosity unique to our moon, but a universal phenomenon shaped by the same physical laws everywhere in the cosmos. We reflected on the timescales involved, the billions of years of patient braking, the slow recession of the moon, the gradual slowing of the Earth. We contemplated the future, when the moon will be farther away and solar eclipses will end, when the sun will die and the Earth will grow cold. And we found in all of this a sense of wonder and peace. The moon is locked. It will remain locked for as long as the Earth and moon exist. This is not a limitation or a constraint. It is a gift. It is a window into the workings of gravity, a symbol of cosmic stability, a constant companion in the night sky. The lock connects us to the past, to the billions of years of history that shaped our solar system. And it connects us to the future, to the eons yet to come. And now, as the night deepens and your thoughts grow soft and slow, let the image of the moon fill your mind. Picture it hanging in the sky, silver and serene, showing you its familiar face. The same craters, the same seas, the same gentle light. It is there, right now, locked in its eternal dance with the Earth. It is there, and it will be there tomorrow and the night after and for countless nights to come. The strange truth about the moon's motion is now known to you. It spins, but it spins in perfect time with its orbit, a synchronization achieved over billions of years. It is not stationary, it is dancing. And every night when you look up and see its face, you are seeing the result of this dance, this ancient, gentle, gravitational waltz. So let yourself relax, let the tension leave your body, let the Rhythm of the tides, the rise and fall of the oceans echo in your breath. The moon is watching over you as it has watched over every human who ever lived. It is a guardian and a guide, a symbol of constancy in a changing world. And as you drift toward sleep, know that you are part of this great cosmic story. You are made of atoms forged in stars, living on a planet shaped by gravity, looking up at a moon that has been locked in place for longer than you can imagine. You are connected to everything, part of the same web of matter and energy that spans the universe. Rest now. Let the gentle wonder of the cosmos carry you into dreams. The moon is there, locked and luminous, a friend in the darkness. And tomorrow, when you wake, it will still be there, continuing its dance, showing you its unchanging face. Thank you for spending this time with us, exploring the gentle mysteries of tidal locking. If you found this journey peaceful and informative, we would love for you to join us again. Consider subscribing to the channel so you do not miss future explorations of the cosmos. And if you have thoughts or questions about what we discussed tonight, feel free to share them in the comments. We always enjoy hearing from fellow stargazers. For now, rest well, sleep deeply, and let the moon watch over you through the night. Good night. There is one more thought to share before we part ways for the night. It is a thought about the nature of understanding itself, about what it means to truly know something. When we say we understand tidal locking, what do we mean? We have learned the physics, we know about gravitational gradients and tidal bulges, about torque and braking and synchronous rotation. We can describe the process mathematically, trace its history, predict its future outcomes. In one sense, we understand it completely. But in another sense, understanding is always incomplete. We understand tidal locking in terms of gravity, but what is gravity? We can describe it mathematically, using Newton's equations or Einstein's general relativity. We can measure its effects with exquisite precision, but we do not know why gravity exists or why it has the properties it does. The fundamental nature of gravity remains mysterious. And the same is true of every physical law. We can describe how the universe behaves, but we cannot explain why it behaves that way and not some other way. The laws of physics are not logical necessities. They are empirical facts, discovered through observation and experiment. We know that mass curves space-time and creates what we call gravity, but we do not know why mass has this property or why space-time is curved rather than flat. This is not a failure of science, it is simply the nature of knowledge. Every answer raises new questions. Every explanation rests on assumptions that themselves require explanation. The chain of why goes on forever, or at least as far as we have been able to trace it. At some point, we simply have to accept that this is the way things are, that the universe has these properties and not others, and that our task is to discover and describe them as best we can. Tidal locking, then, is a phenomenon we understand deeply but also incompletely. We know how it works. We do not know why the underlying laws that make it possible exist. And there is a kind of humility in this, a recognition that our knowledge, however vast, is always partial, always surrounded by mystery. But partial knowledge is still knowledge, and knowledge can be beautiful. The fact that we can understand tidal locking at all, that our minds can grasp the patient work of gravity over billions of years, is itself a wonder. We are small creatures on a small planet, and yet we can contemplate the cosmos, can trace the motions of moons and planets, can peer into the deep past and the far future. This is the great gift of consciousness. Not that we know everything, but that we can know anything at all. The universe is vast and ancient and strange, and yet here we are, making sense of it piece by piece. The moon's locked face is one small piece of that puzzle, one window into the nature of reality. And through that window, we glimpse something profound, something beautiful, something worthy of our attention and our wonder. So let your understanding rest easy. You have learned something tonight, something real and true about the cosmos. You have traced the history of the moon's rotation, explored the physics of tidal forces, contemplated the fate of distant worlds. This knowledge is now part of you, woven into your understanding of the universe. And beyond the knowledge, there is the feeling. The sense of awe that comes from contemplating cosmic timescales. The comfort of knowing that the moon is there, constant and reliable. The peace of understanding that you are part of something much larger than yourself. These feelings are just as valuable as the facts, just as important as the equations. As you settle into sleep, let both the knowledge and the feeling accompany you. Know that you understand something true about the moon. Feel the wonder of being alive in a universe where such understanding is possible. The two go together, fact and feeling, science and poetry, the rational mind and the wondering heart. The night is deep now and the stars are bright. The moon hangs in its place, locked and luminous, showing you its ancient face. It has been doing this for billions of years, and it will continue for billions more. You are a brief visitor to this cosmic scene, here for a moment in the vastness of time. But in that moment, you can know and feel and wonder. You can participate in the great human project of understanding. You can look up at the moon and say, "I know why you show me the same face. I understand." And in that understanding, there is a kind of communion, a connection across the void. The moon does not know you are watching. It has no mind, no awareness, no sense of being observed. It is simply rock and dust, shaped by gravity and time. And yet, in your awareness, the moon becomes something more. It becomes meaningful. It becomes a symbol, a companion, a source of beauty. You give the moon its significance by looking at it and wondering about it. This is what consciousness does. It transforms a universe of matter and energy into a world of meaning and value. So rest now, knowing that you have done something important tonight. You have looked at the universe and asked why. You have sought understanding and found it. You have connected yourself to the great chain of thinkers who, over centuries, have built our knowledge of the cosmos. You are part of that tradition now, a link in that chain. And tomorrow, when you see the moon again, you will see it with new eyes. You will know its secret, the strange truth about its motion. You will understand why it shows you the same face, why it dances in perfect time with its orbit, why it has been locked in this configuration for billions of years. And in that understanding, you will find a deeper appreciation for the beauty of the night sky. Sleep well, dream of moons and planets, of gravity and time, of the slow dance of worlds across the cosmos. The universe is full of wonders, and you have glimpsed one of them tonight. Let that glimpse carry you into restful sleep and peaceful dreams. The moon is watching. It always watches, locked in place, a sentinel in the sky. And as long as the earth and moon endure, it will continue to watch, showing us its familiar face, a friend in the darkness, a guide through the night. Good night, and may your sleep be as deep and peaceful as the silence of space. And so we come to the very end of our exploration. The story of tidal locking is complete, at least for tonight. We have traveled from the familiar sight of the moon in your window to the farthest reaches of the cosmos, where distant worlds orbit alien stars in locked embrace. We have traced billions of years of history and glimpsed billions more of future. We have found in the simple question of why the moon shows the same face, a doorway to understanding gravity itself. The universe is generous with its mysteries. Every answer opens new questions. Every understanding reveals new depths of wonder. Tidal locking is one thread in a vast tapestry, and tonight we have followed that thread as far as we could. There is always more to learn, more to discover, more to appreciate. But for now, this is enough. The moon is there. The lock holds, the dance continues. And you, dear listener, are part of it all. A conscious being in a conscious moment, wondering at the beauty of the night. Rest now. Sleep deep, dream well. Until next time,